Okay, in section 7.3 we're going to be looking at logarithms and the derivatives of logarithms. First of all, since we're talking about logarithms, we're going to want to know what they are, but before that I'd like to know a little bit more about logarithms in knowing where did they come from and why do we even care about them. So first of all, back before we even had pocket calculators, which is like 30 or 40 years ago now, the answer is pretty simple. We used and needed logs to compute powers and roots with any degree of accuracy at all. And a lot of times we even use multiplying, dividing, regular old numbers. We would make it easier by using logarithms. And in the back of an old algebra text you would find pages and pages and pages in an appendice of logs of numbers. And anymore you don't see that in books because of course now we have our pocket calculators. Back in the 1600s there was a big scientific revolution, but before that revolution, right before that revolution, scientists and especially astronomers used to spend very large amounts of time crunching numbers on paper. And while this is very enjoyable, they were very productive about the big ideas because they were kind of more focusing in on the minutia, the detail of those crunching of numbers. So what they did was invent this idea of a logarithm. And when they did that, it cut the time they spent doing arithmetic so far down that it gave them a longer productive life, meaning they did more, they found more, they discovered more in their lifetime because of the logarithms than they would have been able to because they would have spent so much more time just crunching numbers. The slide rule, you probably have never used a slide rule, but even on this campus we used to have a class called the slide rule class, and you would go there and learn how to use the slide rule. But the slide rule was used to find computations very quickly, and it was based on logarithms as well. And today we no longer use logarithms to just do routine number crunching like finding roots and finding powers, but we still do have some very good reasons for studying logarithms. So why do we care about logarithms? Well, one reason we might care about a logarithm is we can use it to find, let's say, the number of payments on a loan or the time it takes to reach a particular investment goal. So you might be able to say I have $10,000 starting and I want to have $1 million. How long will that take at this particular interest rate? So you could use logarithms for that as well. Logarithms also model many natural processes, particularly in living systems. First of all, just even sound while you're listening to this, we perceive loudness of sound as the logarithm of the actual sound intensity. And decibels, you know, the decibels of a speaker, etc., are a logarithmic scale as well. And the same way with light. We perceive and measure on a logarithmic scale for that. For you chemistry majors, we measure pH or acidity of something with a logarithm as well. The pH of something is the negative logarithm of the concentration of the free hydrogen ions, of course. We measure earthquake intensity on the Richter scale, which is a log scale. We analyze exponential processes that we talked about in the last chapter. For instance, growth of bacteria in a petri dish, decay of a radioactive isotope like carbon-14 dating, the cooling of a dead body, kind of some CSI stuff, the spread of a disease in a population. All those are some different examples of looking at analyzing exponential processes with logarithms. So those are some reasons where, or some places where they came from and why we care about them, because they have so many different applications. The next thing we want to look at is what is a log? Well, first of all, let's look at some notation. Log base b of x is the inverse function of b to the x. And vice versa, because we know from the previous section that if a function has an inverse, that inverse and that function have a nice relationship. They're inverses of each other. So as with b to the x, if you'll recall, there's some restrictions here for b. b has to be positive and b cannot be equal to 1. Well, the same holds true for log base b of x. And that's how we read this, log base b of x as well. Now, a couple side notes here, and this is very important. Always, always, always put parentheses around the arguments of your log functions. Now this is log log. If you write log, it means log base 10, it's implied log. If you write ln, it means log base e. So of your log functions that we want to look at there. So for instance, we write log base b of x, we write log base b of x plus 2 in parentheses, log base 6 of x squared in parentheses because that's the argument, log base 10 of 1,000, argument is always in parentheses. This will help just keep things straight and clarify what our arguments are when we're working with some different expressions. Let's go ahead and look at one particular base that we really like to work with, and that's the natural log. It's called the natural log because the base of this log is e, which is the natural number e. So we denote this log base e of x. Now instead of this log base e, we've kind of shortened this to ln of x. So ln of x means log base e of x. And again, it's called the natural logarithm because it has a base of e, and e of course is the natural number. So let's go ahead and look at a quick characteristic here. If you grab your calculators, the natural log of 12 is about equal to 2.484906665. Okay, well that's interesting. Therefore, e to that same value, 2.484906665, is approximately equal to 12. That's what the natural log relationship is. And this kind of brings up a really important point. A log is nothing more than a rewrite of an exponent. And we can see this in the example up above. This is a very, very important point. A log is nothing more than the rewrite of an exponent. So what we had here was this nice log expression, and we rewrote it in terms of an exponent. So it's nice to be able to work back and forth between the log notation and the exponential notation. So let's go ahead and look at that a little bit differently. Let's say we have an expression x equal b to the y. That's my exponential notation. How do I rewrite this in log notation? Well, this is the base of the exponent, and this will also be the base of my log expression. So this is going to be log base b of x equals y. Now, first of all, it doesn't really seem to make sense here exactly what's going on. And the way I usually remember these is it runs counterclockwise. B to the y, b is my base, y is my exponent, is equal to the argument of the log. So that's usually how I keep track of them. Let's go ahead and look at a for instance here. For instance, 5 squared equals 25. That's one we all know. If I were to write this in log form, the base of this exponent is 5, so that's going to be log base 5. Now 5 to the second power is 25. So log base 5 of 25 is 2. And again, they're just rewrites of each other. A log is nothing more than the rewrite of an exponent. It's kind of important to keep that in mind because sometimes it can get a little bit complicated. Okay, let's go ahead and look at a couple of definitions that are pretty useful. Now we're going to be able to establish these definitions after we learn our laws of logarithms, if you're interested. First of all, one is b to the log base b of x is just equal to x. This is just a very complicated way of writing x. And here, if you notice the bases, base b here, kind of, not really, but kind of cancel each other out. And whatever this argument is up here will be what is over here on the equality. So this, if this was b log b, b to the log base b of x squared would show up over here. And there's also another rewrite. Log base b of b to the x is equal to x. And again, we don't quite know our laws of logarithms yet, okay, but as soon as we see some of those, it'll become a little bit more clear as to what we have going on here. A couple more formulas to keep in mind. These are our change of base formulas. Sometimes we might be working in base 2, which, you know, for a CS major that's pretty important. But sometimes we want to switch it to the common log, which is base 10. Well, how do I make those switches? Well, log base b of x can be rewritten, and notice here what changes is the base. Log base a of x over log base a of b. So if I had log base 10 of x and I wanted to switch this to log base 2, I would have log base 2 of x is equal to is divided by log base 2 of 10. Okay, so that's just a quick way to rewrite. And this one is a little bit more commonly used. Log base b of x is equal to the ln of x over the ln of b. This one is used more commonly because we don't work in a lot of other bases other than the e in calculus. We do sometimes. Natural log is most common though, so if we do have something in another base, we do like to convert it to log base e whenever we can. Let's go ahead and look at the graph of this function and its inverse. So let's go ahead and look at e to the x. We looked at this in a previous section. So when we're graphing e to the x here, the important thing to remember is this nice hinge point. If I plug in a 0 for x, I get e to the 0 is 1, and I have this nice hinge point, and then I have this exponential growth occurring. So this is the graph of e to the x that we've looked at before. Now, let's go ahead and look at the domain of e to the x. So let's be careful what we're working with here. The domain of e to the x, as you can see, are all real numbers, negative to positive infinity. I'm covering the entire x-axis here. The range of e to the x goes from 0 to infinity. And of course we never bracket infinity, so it goes from 0 to infinity. Also, we have to keep in mind I'm working with the inverse function. So the inverse of e to the x is the natural log of x. Okay? Well, remember, between a function and its inverse, what we do is we swap the domain and the range. So now let's swap the domain and range. When we swap the domain and the range, I'm going to be working with the ln of x now. So for the ln of x, the domain will be the range of the e to the x function. The range will be pulled from the domain of the e to the x function. So this is kind of giving me an idea. This is telling me, the x values that I can plug in are only between 0 and infinity. Well, that means I'm over here somewhere in either the fourth or first quadrant for my inverse. And the range will go from negative to positive infinity. That means it will go from negative to positive infinity. So I'm thinking it's going to lie in both quadrants. Well, let's go ahead and look at one of those important hinge points. This point right here is the point 0, 1 on the e to the x graph. Well, remember what happens. You transpose or switch the domain and the range, so this becomes the point 1, 0. I'll sneak it under here. And it reflects across the line y equal x. So it's going to look something like this. And we can see from here, domain 0 to infinity, range negative to positive infinity. It's going to keep growing as we see here. Now it's never going to cross the e to the x line, but I do have this line right here that shows that reflection. There's also a few other interesting characteristics about the graph of the log function that I'll note here as well.